So it's a real pleasure to introduce Raffaele Mezzenga. Also, he's a very nice person, a very talented researcher. He has a very long career of success and a very nice person with whom to collaborate for years. Raffaele is a pretty wide heterogeneous background. So he's started his PhD in Lausanne, doing working on polymer physics, that's the better side, at least from thermodynamics. Then he moved to Santa Barbara for a postdoc, and afterwards he went back to Switzerland, but he went on the English side, working for a period as a senior scientist at the lab. And there, I think it was when you start being interested in food-related stuff, biomolecules, so, and then after that, you went again back to full academia, starting as a professor at the University of Freiburg, and finally PhD as a full professor. So today's talk is going to be, I think, most fundamental, and to start to reflect the most fundamental side of Raffaele's research. But I want to highlight here that it also is a very nice track of translation. So looking for practical application of his words, and he can count on a few startups and patents spreading on applications such as creating particular kinds of gold or water purification or iron delivery and so on and so forth. And so I just won't take any more time. I really just welcome Raffaele and please the research.
Thank you, Salvo. Thank you very much for the introduction. Can you hear me well? So thank you very much for the introduction, for the invitation. I'm very happy to be here. What I would like to do with you today, yes, the talk will be rather fundamental. I decided to keep it on the fundamental side. And what I would like to do is just to share with you some of the understanding that we gain on liquid crystalline phase separation, and I will put it in a context with I'll try to make a parallel with liquid phase separation. That's why I put it in red, the C, just to make the difference, I like the difference from the very beginning. And our understanding comes mostly from playing with amyloid and nanocellulose fibrils. They have, these are filamentous colloids which have analogies and differences. One is protein-based, the other one is carbohydrate-based. Of course, one is left-handed, the other one is right-handed. But most of the thing I'm going to tell about is about amyloid and nanocellulose for us is just a benchmark. Okay, so let me start with liquid phase separation. Okay, and I think this slide this is a diagram. I think from my I don't have any other electronic device. Sorry. Yeah, let me play this again. So I take this from my PhD. Okay, so now you can calculate how old I am if you're interested. And what I'm showing you is the free energy of mixing versus composition of a dynamic polymer plant. And you see this change, this convex, you get convex and concave, and I don't know what is wrong. The microphone.
Yeah, I think we can find it.
Okay. Sorry. No problem. You know, I'm Italian, so I like to move ends. That's why I prefer to this at the back of the microphone. But that's fine. So what I'm showing you is just that it's a number of different parameters. The shape of the free energy can change, And from this, you can calculate the phase diagram. We all know how to do that, right? So you have to look at the points where you have equal chemical potential. This gives you the binodal line. The inflection point gives you the spinodal line. You just have to do that for every temperature time or so on. And then basically you end up with this kind of phase diagram where this is, so to say, enthalpy could be the inverse of the temperature. In this specific case, it's the fluoride parameter, and you can work out the phase diagram. So why do I tell you this? So first of all, this is already 25 years ago, and by doing that, I'm doing nothing else than using a form or another of the fluoride Higgins equation, which is a cornerstone of the physics. Of course, you recognize this is the entropy part, this is the enthalpy part, and so on. Now, this equation here, in a form or another, was already appearing in the book of Paul Flory, Principle of Polymer Chemistry, in 1950. Okay, so we're talking about more than 7 decades ago, and what is in the book, we tend to understand it as a common knowledge, right? So, what is new with liquid phase separation? That is, there are at least 7 decades of very fine understanding of it. Well, what is new is that liquid phase separation is being rediscovered very recently in the context of biology. And this is both within the cell and in the extracellular domain. In the intracellular domain, there have been class surveys or condensate involving DNA and proteins in the nucleoplasm. In the cytoplasm, it's mostly RNA and protein. Some examples which are very notable are organelles, stress granules, and so on, which are membraneless, so they're thought to evolve through the phase separation, but also in the extracellular domains, there are plenty of examples, elastin, many other biopolymer. Muscles, the idea with the business on rocks, which is supposed also to reach from liquid phase separation when the protein which is excreted by the muscle is excluded out. And all these things, they have commonalities. Of course, you start with a single phase, and then the single phase evolves into 2 phases where you start to have droplets which are rich in the protein or the macromolecule are being depleted from the phase. Okay, and this is a spontaneous phase separation mechanism. Now, the question I want to address today is this valid for rigid biopolymer? Okay, do we have the same type of phase separation? Of course, from the title, you already understood that the answer is not. But more precisely, I should say that the answer is it depends. In fact, it simply depends on how rigid the polymer is. And this is just the one summary slides that I have from polymer physics classes. If you have a polymer where the contact length is much larger than the persistent length, it's thought to be is a flexible macromolecule or a polymer. If the contact length and the persistent length start to be about the same length, this is a semi-flexible polymer. And of course, you can have the case where the persistence length is much larger than the contour length, and this is simply the definition of a perfectly rigid polymer. So liquid phase separation, of course, in this domain, but when you move to semi-flexible, even rigid polymers, you switch from liquid phase separation, which is more into the topic that I'm going to cover today, which is liquid crystalline phase separation. And in fact, this is much more common than you might think. There are a lot of biological systems or biological filamentous colloids that do follow this mechanism of phase separation. There we talk mostly about amyloid fibers, but another very widespread example is nanocellulose. Filamentous viruses is also a very interesting system because these are genetically perfectly monodispersed body length cross section. But there are many other examples: DNA, collagen, active microtubule, there are most rigid filamentous colloids you can think of. They all follow pretty much the physics I'm going to discuss today. So now the question is, do we have liquid-liquid interface? We have a demixing mechanism in biological filamentous colloids or rigid polymer in general. And to answer this question, I have to go back to a theory which is even before the one of Wolfgang. This is a seminal paper in soft condensed matter. It's a paper by Lars von Sager in 1949. By the way, a small anecdote that Lars von Sager from that he never got a PhD, but he got the Nobel Prize. So probably I don't know, the standard for a PhD from that must be extremely high. But this is one of the seminal papers by Lars von Sager. He did a lot of other things, but this is a paper I like a lot. Because already back in that time, von Sager understood that the suspension of colloid, filamentous colloids, is better understood not in the real volume, but in the excluded volume. And the excluded volume of a rod, I mean, we all know what the volume of the rod is, but the excluded volume of the rod, which is freely rotating on the plane. Why on the plane, not on the sphere? Well, simply because conservation of angular momentum. The excluded volume will be now the length to the square times the diameter. Okay. And now what von Sager does, and the paper is actually more than 80 pages of equation, but the sense is that when the total excluded volume, so this is the concentration times the excluded volume of one drop, reaches critical value, you have the first order transition, okay? And you have two types of values for, we calculate these two values for infinitely long cylinder, where you can drop the Farrer-Virial coefficients. Basically, the first one is 334, 449 for the second. Now, if you pop in the number of objects per unit volume and the excluded volume this way, this can be simply readapted into this expression here, that there is a first order transition when the volume fraction reach one of these two values times the inverse of the aspect ratio. Okay, and because the values are two, these are two bifurcation points, effectively this condition divides the phase diagram in three regions. If you are below the first one, you are in the isotropic phase. The density of rods is still low enough, but they're freely rotating here. If you are, if you cross this first condition, then you have isotropic plus nematic. You have two phases, and if you cross the second condition, you are fully nematic. So all the rods are aligned along a common director. And the part I'm most interested in is the one in the middle, because of course you go from one phase out of this way or this way into two-phase system. So you must have at some point some kind of binodal, of course, binodal. Okay, and this is the thing that I will bet on today. So how can you enter into this region? Well, you can do two ways. You can have other filamentous colloids to grow, or you could start with something which is very long and it's broken down. In both cases, from left or right, you go from one phase to two-phase system. And this is a bit counterintuitive like that, simply because this is the inverse of the aspect ratio. But if I simply now renormalize, this is the volume fraction that appears here, times the aspect ratio. Now this reduced volume fraction can be very large because this aspect ratio is very large. And now you see this is now in the right sense. If the fibroid goes from left to right, this gets smaller. You go from right to left. So again, from two single phase into two-phase systems. And how do you do that? Well, again, before I ended, I want to highlight some major differences between LLPS and LLCPS. So again, this is the same phase diagram I opened my talk with. The external phase is the binodal line, the inner phase is the spinodal line. And here, in this case, if you have a given Fourier parameter, say a given entropy, the value, would be temperature. You have a second to the phase diagram, for example, this is taken at 1. Then it's very clear you have all what you need to know once you know which composition you have. For example, if you are on the extreme left, outside these 2 points, you know that you are in a stable region. If you are between the binodal and the spinodal, you are in the metastable region. If you are in between the 2 spinodal points, you are in the unstable region. So at that concentration here, you know precisely how the morphology of the system is going to evolve. You know where you have a single phase, you know where you have nucleation and flow, you know where you're going to have spinodal decomposition. In the case of liquid crystalline phase separation, the story is very different and rather more complex because counterintuitively, it depends on the initial state. So it's not enough to say that this is again a scale of concentration. I told you that the first one is 334. So here you will go from 1 phase to 2 phases, metastable. This will tell you, yes, nucleation and growth. But only if you start from the isotropic phase. If you start from the pneumatic phase, in this region you will be simply unstable. So that means you will have less spinal decomposition. And when I started to work onto that, I was so confused because how is possible if you're looking at thermodynamics, at least depend on the initial state. But the answer to that is that this is a free energy that you can express simply. This is a parameter, if you want, as a function of the concentration. But in this case, the free energy is a function of the concentration, but it's also a function of the order parameter. If you look into the way on the right, the volume, that you have a term, which is a function which is a function of the order parameter, and the other term are the term that depends on the concentration. So you have 2 variables. And you can be very well in a region where the free energy is convex if you do the second derivative with respect to the concentration, but it's concave if you do it with respect to the composite, the order parameter. So this tells you that it's not enough. You have to see what is the initial state, what is the derivative versus S, the order parameter, what is the derivative versus composition. So at 3.5, you could be very well forming droplet which are concentrated in problem evolving in a continuous matrix, which is isotropic. But if this is if you start from the isotropic or spinodal, if you start from the pneumatic. For the other way around, if you go beyond 4, the isotropic becomes unstable, the pneumatic is stable, then you have spinodal decomposition if you start in the isotropic phase and you have nucleation and growth. Now, isotropic diploid droplet within the pneumatic phase starting from the pneumatic. Okay, so that's counterintuitive, but simply they reflect the way the free energy of the system, excess free energy, is written as a function of both the concentration and the order parameter. Okay, so with this in mind, now I want to give you some example of how to enter the phase diagram in one way or another one. So I'd like to give you a few examples. Most of them will be based on nucleation and growth. Some will be based on spinodal decomposition that will have a surprise in the end. But I want to show you what are the options to navigate this phase, the phase diagram. In this case, mostly with amyloid. So the first one is typically the way you will do it is you start with a system which is a this concentration in vortex and you are in an isotropic supersaturated solution, and you start to see how the system evolves. Let me tell you first which kind of amyloid we use. So this is my favorite protein, is beta-lactoglobulin. This is the globular protein which is most commonly found in meat. Calcium is actually an aggregate of calcium phosphate and other proteins, and it's not globular. This is really a globular protein. And is a waste problem. If you use cheese to make, if you use milk to make cheese, whatever is left in the serum is mostly enriched in this product. So this product is considered, this whey is considered a waste. And in Italy, for instance, we use this serum to make a special type of cheese, which is called ricotta. I'm sure that you also know it. But it's waste because this cheese lasts very short time and it's very difficult to exploit. So in Switzerland, about half of the whey produced in Switzerland, for example, is encountered in the big dairy industry. This waste. So I like this product mostly because it's super cheap. You can do a lot of things. Most of our technology that I will not discuss today are based on this product. Today, I just want to focus on the physics because it's very interesting also in that aspect. Of course, we don't use the product in the native state. We have to unfold it, and this we do it thermally. Well, 80 or 90 degrees, we use acidic pH to hydrolyze the product. Now, this is broken down. The native product is about 18,000 Dalton. Depending on our presence pH, you chop it down 2, 3, 4 times. So you now have fragments of 2, 3, 4,000 Dalton that reassemble into oligomers. They have one depolymerization into product filament. Different product filament get attached to each other and they twist. Okay, and they form major food amyloid fibrils. This is a coarse-grained molecular dynamic representation. This is one of the first paper we published in the field. This is 2 strands, this is 3 strands, this is 4 strands, we see 5, 6 and more strands, and I have a summary here. Now, of course, the cross-section of these fibers is different, but the important thing here is one to keep in mind for the remaining of the talk. The twist angle is a constant. Okay, so if you have 2, 3, 4, 5, and so on, the pitch divided the length is almost a constant. I say almost because Salvo published a paper a few years ago. It's not exactly linear, but I mean, for most of the thing I'm saying is preserved. So that means that the twist angle is a constant, and because the twist angle is a constant, the twist power of this colloidal object is a constant. If you want to twist things. And now what you have to do is simply take the fibril, break it down, and you have to break them down significantly. The persistent length is 2 micron in average. You have to go like 500, 600 nanometers, so you have to be 3, 4 times below the persistent length. Now you have really have a rigid object. Another reason why you have to break it down as much as you can is because you see, this is the window, according to Gonzaga, where the liquid crystalline phase separation is visible. So it's the inverse of the aspect ratio. The more you break it, the larger is the window where you can start to look at them. But if you do that, then it's really a new world that opens up. These are some of the droplets we see in liquid crystalline phase separation of the system. Spindle-like droplet, radial pneumatic, uniaxial cholesteric or chiral pneumatic, radial cholesteric. This is multi-grain. This is 2 phases. This is isotropic. This is the cholesteric phase. The cholesteric phase can have very interesting focal conical defect. This is a multi-grain and so on. And I will spend weeks discussing these images, but I only have 40-45 minutes. So I'll just start to look, for example, at the simplest one, which is this one, which is already extremely complex because we are used to think of droplet as a spherical object. But in this case, you have a pneumatic field that would like to, is uniaxial, so would like to have a cylindrical object. Surface tension wants to close it into a sphere. What do you have in the end? If you minimize things, you have like a rugby ball. Okay, but for this rugby ball to emerge, the surface tension must be extremely small. Okay, and if you make a few calculations, where you could see, for instance, that you calculate the change in entropy between a freely rotating rod here and a constrained rod here, and this
changing entropy times temperature over the volume, the length of an interface is lying as a surface over area. This is the interfacial tension that you can calculate this way. Or you measure it, you get the same answer. We can set the 10 to the minus 7 Newton per meter. And just to remind you, what oil in water is 10 to the minus 2. So there are 5 orders of magnitude difference. And this is simply because in oil in water, the molecule of oil and molecule of water don't like each other. They have an energy of exchange divided the surface area, that's the surface tension. There is no such a thing here. This is amyloid fibers outside, amyloid fibers inside. It's just a delta distance. And if you calculate the surface tension this way, this is the first big difference with the liquid phase version. Entropy as an entropic, or the surface energy as an entropic source, as an entropic origin. That's why it is much, much lower. Now, note, for example, here there are people working with Dextran and PO, the still liquid phase version is still because Dextran and PO do not like each other, it's still enthalpic. So in that case, the surface tension is still very low, but it's tend to be 1 to 2 orders of magnitude more. So this is an extremely low one, can be even lower than that, can be even 10 to the minus 8, depending on the concentration. And in fact, it's so low that it has a lot of very interesting aspects. So for example, this is a microfluidic chip. This is designed to have the spraying rate constant along the channel. And look at the droplet. They come, they stretch, okay, they rotate, and they relax. Okay, and they stretch a lot. Not only they stretch, if they come close, they rarely coalesce because there is such a low gain in making two droplets into one. And if you look at that, I mean, this is some of these droplets, they stretch even 30 times, and then they rotate and they relax back. And look, this is oil water droplet, the same channel, it just goes totally unperturbed. So this is really distinguished of an extremely small surface energy. And of course, the interesting part is not only when they stretch, also when they relax. These are movies that I am trying to display now. These are, we're looking now at the droplet that are relaxing after they have left the channel. And you see they recovered the original symmetry, including the cholesteric. And now if you look at, you can follow how the order parameter evolves. So this is very interesting. This is the order parameter versus time. It's easy if you look at the derivative. And you see the first two cases is monotonic. Here there is a jump. So this last case, there are two landscapes. One is the droplet, the fibers have to realign with the surface, but they also have to twist. And these two different landscapes are they originate in the non-monotonic evolution of the order parameter. So now the interfacial properties are extremely interesting. We have learned that the interfacial surface tension is as an entropic origin, and we have learned that it's anisotropic. It depends on how the rods are aligned towards the interface. So a very good way to probe the interface is actually to probe it locally. And one way that we came up recently, which is very interesting, just to use optical tweezers. So we have droplet. We push, actually, we block the probe particle with the laser trap, and we move the droplet towards the probe. So this is how it looks like. Okay, the trap is on, so the probe particle cannot move. We push the droplet against. You see there is a small indentation, and all of a sudden we release the trap, and this is pushing away. Okay, and if you do so, here we are extremely low Reynolds number, so the only force, there is no inertia essentially. This is the drag force, and the drag force is just the push that the prop particle receives, which has a term in the surface tension and the other term on the elasticity. Okay. Now the interesting part is that this is how we can solve, because of course we can measure the trajectory, the distance versus time. This is the first one. The differential equation is very simple solution, and now the decay exponent it brings in all the properties of the system. So there is the viscosity, the size of the object, interfacial tension, and the elasticity. And for what I just said, that not only the surface tension but also the elasticity change if the rods are orthogonal or parallel. So now what you can probe either this guy or this guy, depending on the design this curve. For example, you can have, if you decide to probe splay, okay, so splay if you have a deviation of rods that converge, so you will approach the droplet this way. Bending is if you have a bending of the magnetic field. Okay, so you will go on the other side of the bend. So, for example, in this case, if you want to probe splay, you approach the droplet this way. If you want to probe bending, you approach the droplet going on the other side. And then again, you measure the evolution of the displacement versus time. And what the only fitting parameter gives you is basically which constant that you probing on display or bending mode. And this works beautifully. So this is just to give you the small, okay, this is for, this is amyloid fibrils, this is nanocellulose. The scale is in piconewton, and look, the large bar is the uncertainty on the same system, done with different measurements, okay? And you see the small bar is the precision of the measurements that you get both on the K1 and on the K3, depending on this curve. So this is the first thing is that because we are not looking at liquid phase inversion and liquid phase inversion, the interfaces of this droplet are extremely different. Okay, they are anisotropic, both in the surface tension and both on the mechanical elastic properties. And now, as this particle go through nucleation and grow, the symmetry of the rods of the fibrils inside the droplet change versus time. So the volume change, the symmetry of the magnetic field change. So if the particle is very small, this is in the early time, we know that the fibrils are all aligned perfectly in an homogeneous way. Why do we know that? Because if we rotate the polarizer and the analyzer, we can find conditions where we have full extinction. Okay, so this is totally black. That means that at this rotation, either the polarizer or the analyzer are 90% orthogonal to a single director. If they grow, I don't know whether you can see it, but you see extinction, but you never see full extinction. Even here, unfortunately, you cannot see it well, but there are boundaries where you still see signal, which tells you that the fibers start to follow the interface. So there is bending here, and there was no bending here in the magnetic field. But of course, if they grow enough, they start to twist, and you see these fringes that develop. So why is the symmetry changing with time? And if you look at the total free energy in the system, and I put it in 3 different colors to make it more obvious, there are 3 main contributions. The first one is related to elasticity, which I was telling you, splay and bending. Okay, and of course, if I do it this way or I do it this way, I use the same deformation. That's why this came in the same way. I have put it in the same term assume that the two constants K1 and K3 are similar. I showed you before that they are very, very close. Then you have another term which is the surface energy. But the surface energy, this is the usual guy. Now, because we have a possibility to have different orientation, we have an isotopic and anisotropic term, which is this is called the anchoring stretch, and this is basically the aspect ratio. So if you have it orthogonal, this is 1. If you have it parallel, this is 0. And then we have a third term. This is the spontaneous wave of the chiral nematic phase. This is the effective twist angle. So you have 3 terms, 3 different colors. And now you have small r, big R, because these are like rugby ball. Okay, they are 2 different radii. But if you forget about that for a second, think about only one size. You see that this case like r to the 1, this case is r to the 2, and this is r to the 3. So as soon as the particle cross, the wave, the Hamiltonian will shift from left to right. Okay, so the more the progress they go, and the more the terms from the right start to dominate. And now all what the system has to do is to keep the most expensive energetic term. For example, when the particles are very small, this is the guy which controls everything. So all what the system has to do is just put parallel all the amyloids, that there is no bending or spread deformation. Now the system starts to grow, this term starts to take over. What can the system do? Well, kill this term. And then orient parallel the fibers to the interface. And then if the system keep growing, of course you can have a twist now that reach the spontaneous twist, and there is no twist deformation anymore. Okay. And if you equalize the free energy before and after transition, you can work out exactly what are the conditions at which you are expected to see a transition. For example, this is the aspect ratio. You expect the homogeneous to bipolar transition when the volume over the aspect ratio is equal to this object, so it's proportional to the splay/bending constant over the anisotropic part of the surface tension, and you have the bipolar to polysteric switch when is the other way around. Here you have the surface tension. This is the twist constant, and this is the score of the wave vector. And one of the reasons that it took me so long to publish this paper is there are many reasons for that. But one of the referees was saying there is no bipolar polysteric transition. They are both nematic. One is the twisted form of the other one. There is no such transition. But in fact, with a lot of battle, we could convince the referee that there is this transition. For example, this is a work which I love. It's from a group in Milano, Tommaso Bellini. This is DNA, and you see green and red means left or right-handed DNA. It's a simple one phase, but the concentration of DNA changed. And so you see, you can go from right-handed to left-handed, and then when you cross the zero on the way back to means the periodicity is infinite. This is a pure nematic phase. So at least you could argue, yeah, maybe this is a second order transition, but there is a transition. And I will show you that this is actually first order. The second order only because they have one phase. If you go to 2 phases, I'll show you this is first order. So this is one evidence that this transition should exist. For me, this one is the most beautiful evidence. These are 2 droplets that they collide, and when they drop, this is a sudden event. Okay, droplets originally have a bipolar integration. When they collide, they change suddenly volume, and there is no exchange in such a small time between the external phase and the internal phase. And what used to be 2 droplets of bipolar becomes a cholesteric with 2 bands. Okay. This is a cholesteric problem with 2 bands, so there is a change in symmetry. Of course, if the particle probe will go from bipolar, you see here, this is a 3 bands, but here this is a long process. It takes more than 20 minutes, so there is exchange between the 2 phases. But this is really clear evidence. And at the end, if you plot all the cholesteric peptide, we see that these cholesteric peptides are only after this transition that we predict. Okay. So now we really start to understand the phase diagram here. We have at least three symmetries as the volume over the aspect ratio change, homogeneous, bipolar, chiral nematic. We do very know well where this transition happened, at least in terms of the main parameters. Then you might ask, okay, what happens if you keep everything going? What do you see at very large volume? And here, so far, I use a scanning form of the Frank-Possin free energy. Then here things get fairly complicated because if you put in the scanning ingredients, you get trapped in the same recipe you've been doing here. I'll show you first what's going on. And this is the pole-scope image. So this is a very nice technique where each color corresponds to this map of the nematic field. So each color gives an orientation of the 2 pi of where the nematic field is there. And you see in the beginning we have uniaxial particle go, you start to see bending. This bending costs energy. Why does the system puts energy in bending? Because if you keep going, eventually, yes, you have introduced bending, but you have given up the gamma omega part of the anisotropic surface tension. So it's what you have seen before. The difference is now that you have a nematic defect in the middle because this bending and display a small radii curvature is so high that it's just not sustainable. It would just melt into a nematic phase. So this is only one color here because this is melting over nematic. And if you try to work out this with scaling, you get back the same transition that you predicted before because you pop in bending and you pop in the interfacial energy. Of course, there is an effect that can make it different, but this is not enough to stay. So here we had a PhD student who was reconstructing the phase diagram with variational theory. And you see, I think this is the reconstruction done with the John matrices and the theory there, it works very well. So we can reconstruct its simulation pretty much what we observed by the experiment. So now what I want to say is that, yes, we do understand the physics now very well. We call it, as I said, we believe with crystalline phase separation. This is a term that we coined a few years ago now, 4 or 5 years ago. It's different from liquid-liquid phase separation. The main difference is that, first of all, you can observe that with one single system, most of the liquid-liquid phase separation is reported in biology. Of course, there is always the background. So it's raw plus folded, but most of the liquid phase separation is protein, DNA, or protein, and array, and more. So it is one component less, but the most important thing is that this is really an entropy-driven process. Okay. And now the question is, since now we know that the split phase separation mechanism can be predicted by neural lines. And if you look at the original paper of Gonzaga, it's fully thermodynamic. Gonzaga doesn't say anything about how to calculate the binodal. But Gonzaga is also the father of non-equilibrium thermodynamics. It's the one who put up the thermodynamic experiment principle, the dissipation function, which introduced transport in, and you can combining that free energy with the dissipation function predicted by another line. I'm not going to go into detail here. If you're interested in that, you find all the detail on this paper by Paride Azzari. But basically, this is how they look like. You have a window, you don't close that as you would do liquid phase separation. This is the isotropic, this is the nematic part. This is a log scale of the volume. So this is the branch which depletes the protein, and this is the branch which can enrich with the protein as long as phase separation proceed. This is the risk scale function of the volume. This is for the amyloid that we tell you about. This is carboxylated nanocellulose. This is sulfate nanocellulose. Each time you change color, you change symmetry at the evolution of the binodal lines evolve continuously. And now we can even know what is the form, what is the nature of the transition according to at least the first classification. And you see, this is the total free energy. We take up the gamma r squared, which is a well-behaving function. So this is all the elastic part plus the anisotropic. And you see, there is a change in smoke versus the volume. At least you can capture that here and here. So that tells you that this is actually the first order thermodynamic transition. And the reason for that is that really this is a two-phase system. The anisotropic part of the surface tension equals finite, zero. Finite, zero. And this jump is responsible for the first order transition. Okay? If you have one continuous phase, most likely this would be a second order transition. We don't know about this one. Maybe the change in slope is just not enough, but there is clearly no question for the other transition. Okay, what about spinodal decomposition? Now, there are two ways you can look at spinodal decomposition. Either you increase the concentration, you go from isotropic all of the sudden to two-phase system, or you can do it the other way around. You can just cross all the phase diagonal fast enough. Fast enough means faster than the nucleation rate of the tectoid, and this should give you access to the spinodal. And I have this, what you see in the background is a movie. I hope it will play. Yes. And you see, this is a droplet, and you start to see at the edge of the droplet, you see struts. And this struts is a signature of the spinodal decomposition. If you wait long enough, you see that now this forms droplet. So let me play that again one more time. In the beginning, you see struts forming. This is spinodal decomposition. You see here. If you wait long enough, you form directly tectoid, which is nucleation and growth. You see now they form directly as a tectoid. Why is that? Well, simply because there's a coupling effect. You have different rate of evaporation. In the middle, you have slow evaporation. So you are entering gently into the phase diagonal. If you go very fast in this you see tectoid. If you go very fast, however, you go directly into the spinodal decomposition regime. And I have an idea how to do that with other terms, but the evaporation is just very convenient for them. Now, I've been telling you about nucleation and growth. I've been telling you about spinodal decomposition. But in both cases, if you look how the morphology evolves, this is nucleation and growth, this is the nucleation rate, this is the growth times the rate, the diffusion coefficient is there. If you have spinodal decomposition, you rather use the Hilliard equation, which gives you the evolution of the concentration profile. The diffusion coefficient is also there. So this slide is there to tell you that whatever you observe is a trade-off between thermodynamic and kinetics. Okay. The only way to observe truly thermodynamic behavior, it would be if you have an infinite diffusive coefficient, which we don't have. And very recently, we came up with a different way to add a heterogeneous colloidal system, which can bypass both nucleation and growth and spinodal decomposition. And it's very simple the way we do that. So we have a system, and we get the system to evolve into reach equilibrium. And this, at the end, if you give enough time, you have the isotropic and the cholesteric or chiral which is sedimented. So this you have reached equilibrium. You just have given the system all the time it needs to reach equilibrium. And now what you need to do is simply you take the nematic phase, you re-extrude the nematic phase into the isotropic phase. And what you form, you have to just fast enough because you break the jet with the Rayleigh plateau. But if you do that fast enough, you're able to generate a gain droplet. And the beauty is that depending on the flow, you can generate droplet again of different size, and again you see different size correspond to different symmetries. This is the nanocellulose you can form directly uniaxial or steric basis. But now this droplet, they are born already at thermodynamic equilibrium because the two phases already have the two branches of the enzyme. Okay, and now, of course, you can do the other way around. You can, if you want, you can extrude the isotope into the pneumatic, and you have negative tactoids. And now the beauty is that you can really test how off you are from thermodynamics. So, on target tells you that in the ideal world you have two phases, one that is branched, the other one is at this time. Wherever you are in between, the system will evolve to this guy and this guy, which is what you see here. But now we know, I showed you before, versus time, the binodal lines and the gentleness slope. Okay? And depending how off you are from the thermodynamic boundaries, you will have the signature of the kinetic becoming more or less prominent in the system. And look at this example. For example, we know that, okay, this is thermodynamic. We know from the other side that if you use nanocellulose diffuse extremely fast. The rods are very small, they're super rigid. You tend to approach already from the very beginning the thermodynamic boundaries. But in the case of amyloids, they are longer, they're more semiflexible, then the shallow slope in the binodal line. So we expect to see the nanocellulose to have more prominently thermodynamic and the amyloid to be trapped in metastable state. And the best way to test it is just to look at the internal structure. We just mentioned the periodicity. So in the case of nanocellulose, indeed, if you do the equilibrium trick or you do the exclusion, you let the system evolve. This is the pitch versus the natural pitch. You see pretty much the same value. In the case of amyloid, though, this is what you will get at the equilibrium. This is what you have if you have inflation and growth. You might have up to 50% difference in the pitch. Okay. So if you put it back now in context, this is the amyloid fibers. If you do the binodal thread breakup, so you take the equilibrium phase, you really screw it inside, you get a pitch of 46 micron, you get inflation and growth, you get 35, 36. This is a significant difference. But if thermodynamic, if you take a job that approach the binodal line, immediately the nanocellulose 16.7, 16.7. So we really now have a trick to bypass kinetics and what used to be before a method to have how do you develop a heterogeneous colloidal system through phase separation for liquid or liquid crystalline. You typically either use nucleation cross by another decomposition. We now know how to make a heterogeneous colloidal system which are born directly at thermodynamic equilibrium. I want to close, very quickly. I told you only this way, fragmenting, but in nature, if you switch to pathological amyloid fibers, it will look from the other side. Okay, and typically, if fibers start to grow, suppose that you are in pathological amyloid, you have, I don't know, A beta concentration of picomolar. This is blocked, but they can grow. So this is a constant, but this is growing. And because, according to Mezzenga, this is an environment, at some point you can start, even if you're extremely dilute, you can always find a sufficiently long fibers that bring TL over B to 334. So this is just there to tell you that if you have an object, and I will skip this slide because this is getting too much into detail. If you have an object which is infinitely rigid, the evolution to go to from one to two phase system is just natural. And we think this will explain why proteins which are extremely diluted, like alpha synuclein, A10, and so on, can drive the system from one phase to two phase. So this could be the origin of plaque in Alzheimer or in Huntington or Parkinson disease. So this is a slide just to summarize. Last year, together with Matt Harrington at McKibb and Ali Seres at FU, we put up a review to explain the differences between LLPS and CPS. This reference gives a lot of biological system where people still get it right, wrong, and say, I talk about LLPS for this guy, but LLPS is isotropic. This is an So if you want to interesting to the system there, or if you want more to focus on the fundamental physics, we spent the last 2 years together with my group and the group of Alejandro Rey and the key to put order into that. I can say that I think we now understand very well the difference between LLPS and LLCPS. And this is my group on a sunny day in Zurich. This is already back a few years. Ahmed, remember the name of this guy, Ahmed Al-Muhammadi. This will be professor in the top university, so one of the best students I ever had. This is Paride, that I had the pleasure to. That is my first PhD student in theoretical physics. Massimo, who left the academia, and Yale is now professor at Hiroshima University. And with this, I'd like to thank you all for your attention and be happy to take the questions. Thank you very much.
Thank you very much for the lecture and time for questions. Go ahead.
Thanks for the talk. I want to explain the thing. So maybe my question is a silly one. You have said that everything is controlled here by excluding volume. Imagine that you can engineer these things in such a way that on one side of the fiber of the road you have something that is very hydrophilic, and on the other side something very hydrophobic.
Yeah.
Could these adaptive or repulsive interactions change significantly the phase diagram?
Okay. Very interesting question. First of all, I am often attacked when I say it's fully topic. And in fact, I should say, I like to provoke a discussion that is predominantly in topic. For example, we all know that two charged rods, they want to align this way because they minimize energy. So if electrostatic is important, you start to see non-entropic effect. These rods are hundreds nanometer long. The divide length is 3-4 nanometers. So we are still poorly on the excluded volume domain. What you're saying is possible. You will trigger enthalpy effect, so that they will guide the twisting. Will just be another trick to introduce a non-entropic effect. There are people who have been working, for example, on adding polymer brushes on the side of the pond, then go again. The C effect, the phase diagram gets more complicated, so it's possible. Okay, thank you.
Thank you. More questions?
Thank you for the talk. Yeah, you have this transparency at the beginning showing the different flexible polymer depending on how the length compared to the system length.
Yeah.
But if you have a liquid crystal phase, probably the persistent length may be much larger than if you have the same molecule in a disorder phase. So I wonder whether you may have some coupling between these two things.
Yeah.
Which becomes liquid because it is liquid crystal. But
yes.
it will be flexible If you just take it.
Okay, okay, thank you for this question. I'm not sure if I give you the right answer, but I will give you one answer. Then you can. I'm trained as a polymer physicist, okay? And when we started to look into this system, I said, okay, the fibers have the persistent length of 2 micron. I break them down to 900 nanometer, 800 nanometer, they are extremely rigid, okay? We see pneumatic, we don't see cholesteric. And that's why I said, okay, that's way below the persistent length. And then at some point we change the method and we go to 500 nanometer, and all of this happened, and we start to see the chiral pneumatic. And I was, of course, very happy. It took me here to get to that point. But why does the system depend so in a sensitive way on the persistent length? This is the thinking of the polymer physics, but in liquid crystal, there is another length which is called the bending constant or bending length, which is the persistent length divided the alpha in the unsighted triangle function, and alpha is 4 or something there. So that means that you have to go significantly below that in order to observe truly liquid crystalline. So just to cut the long story short, if you don't, you asked me about the persistent length. Yes, if you're not way below the persistent length, we believe, and we have done some calculation, at least from a scaling point of view, makes sense. The bending fluctuation of the fiber, which is now below the persistent length, but still bending, is near the long order chiral pneumatic phase, long cinematic phase. So the persistent length and the bending length are extremely important to govern what you see. You are totally right. Still, it took me a few years to get to that point. So.
Thank you. Any more questions? Most of the students are very encouraged to ask stuff. Okay, so I will probably ask a question myself. It's very speculative and just curiosity. So all your studies here have been focused on growth. So you have started from the aspect ratio as being your parameter.
Yes.
What do you think happens to this? The main principles that you find in more fancier states of crystals, where you, I don't know, some magnetic or some other even more exotic stuff. Do you think they still apply?
Okay. Well, I mean, you talk about molecular liquid crystal, or yeah. I mean, if you go, I mean, the beauty of the one-sided theory is that everything is screwed by a screwed volume, so it works when the aspect ratio is huge. Okay, if you start to get the aspect ratio, it's not only the aspect ratio; it's really the length scale. Small, you start to enter into the small molecular, so you start to have other interaction which are not here, dispersion, van der Waals. So other theory will be better than Meyer-Solf will be better than Cyber at some point if you get a very small scale. So of course you have parallel pneumatic phases also for molecular liquid crystal with totally different pitch. But at some point, the one theory breaks down and you enter into molecular theory to describe it. So, yeah.
More questions? So if not, let's thank Raffaele again for.
Thank you.